And so today we are going to introduce purrr, which is really not that much different than what we've learned so far. Okay, basically because I'm only introducing it, right? So I'm very purposefully showing you the pieces of purrr that map directly to the pieces that we've already learned. Okay, so I'm showing you basically the purrr alternatives to lapply and then vapply. Okay, so there are actually 4 functions that we'll learn about that take the place of those 2. Okay, but they're a little easier. But we also need to review lab 1, and then we're going to go through an example of functional programming. So that's the title of this course, right? Functional programming in R. And I don't feel like up until this point, there's really been a very clear definition of what functional programming is. So we'll talk about what I mean when I say functional programming and what that actually looks like. And then we'll work through a small example. Now, because we're at week 3, right, there's going to be pieces of that that are not familiar to you and that might feel uncomfortable. And that's okay because we haven't gotten to all of it yet. So again, the idea is to use some of what we've learned already, specifically the looping parts, and then show you sort of the broad picture. So if you're not following along every piece of that example, that's not a problem at all, okay? So we'll review lab 1, then we'll go through that, and then I will introduce you to purrr, and we're going to specifically contrast it with the base functions we learned last week. And then we will have our second lab, okay? Sound good? All right, so let's start off by reviewing lab 1. And so I mentioned this already before, but I will mention it again because we are, oh, you guys probably on Zoom didn't see my screen, did you? That's okay. It was nothing super important. But what I will do now is walk through lab 1, and just to reiterate, we will not have any, like, you won't have any individualized feedback for any of this. So this is your time to get that feedback. If there's pieces that you are confused about or questions you have, please do ask them, okay? And if you want to follow up later, like, you know, you did it one way and then you see that I'm approaching it a slightly different way, but they ended up with the same answer or whatever, and you just want to talk about that more, that's fine too. Just reach out via email, okay? Just generally, also, I think most of you probably know this from past classes with me, but I don't know how often I explicitly state it. I'm much better about email than I am with Canvas. So if you ask a question through Canvas, I'm going to be a lot slower to respond than if you ask it through email, okay? And this term, I'm a little slower on email too, but I'd usually check it at least once a day. Okay, so the purpose of this lab was to work on looping, right? And then to dig into nested lists, okay? So the first thing that I asked you to do was to run this stuff. So we set our seed, which is basically just going to make sure that all the random number generation stuff is repeatable, okay? So that it will happen the same way every time. Then we fit some model to the empty cars data set, and then we create this nested list. So this list, if we're just looking at it, right, what is the length? What do you think the length of L is, just looking at that? Okay, give me like just a number of fingers in the air. 1, 2, 3. What's the length of that list? Okay, the correct answer is 2. Okay, and the reason is because it just has 2 elements, A and B, right? But it is confusing because this is a nested list. So if you're thinking about this recursively, it's longer, right? And that's because it has the first element of this list is itself a list, right? So A is a list of length 2 as well, right? It has these elements M and V. And B is a data frame. B is the second element of L, right? And it's a data frame that has student and score in it, okay? So we run all of that, and then from the model results, we extract the QR tolerance, okay? So that's the first thing we're gonna do. So what I wanna do is I've already run these, but what I'm going to do is use str on m. Okay. Bring this up like this. So when I do that, I get this big thing that looks like this. All right. And I showed this in class, but you could also do view m, and that will get you this thing. Okay. And so if this is easier for you to look through, that's fine. But either way, I want you to be, so you can click on these things and see what's under them. But basically, you want to look through these and notice you can see the levels, right? So this is a list of 12. M is a list of 12. This is the model output. This is what is returned to us when we fit that model. The first element is the coefficient. The second is the residuals, then the effects, then the rank, then the fitted values, then the sign, then QR. And when we get to QR, notice we have these dot, and then we have this other thing, right? So we have another thing inside QR, which is itself called QR, okay? And this is a number with dimensions 1 to 32 and 1 to 4. So what do you think this actually is right here? What kind of R object is that? A matrix is correct. So we can tell it's a vector of an atomic vector of some sort with this part, right? NUM, and down here, same thing, CHR, right? That's a character type. This is numeric type. But then we have these dimensions of this where we can see it has 2 dimensions, right? So if this is an atomic vector with 2 dimensions, then that means it's a matrix, okay? And so here's the first couple of entries from that. And then within here, notice we have this ATTR dim names, okay? So from this QR thing, nested inside of that are these attributes, and it has dim names, which is a list of 2, okay? And then we have these 2 things. So this is basically the rows and then the columns, okay? 1 to 32, 1 to 32. So these are the row names, basically, and these are the column names, okay? And so, and then it also has within QR, it also has an additional attribute called assign, which is an atomic vector of type integer that is of length 4, right? 1, 2, 3, 4, and it's just 0, 1, 2, 3. Okay, I don't even know what that assign stuff is, right? There's lots of stuff in here that you may not know what it is, and that's fine. It's not a big deal. Again, the purpose of this is to get you to look at this list in this sort of detail, to look deep inside of it, and then try to start to pull things out of it, okay? So if we want to pull out the QR tolerance, notice within QR here, right, it is a list of length 5, okay? The first one is QR. That's the one we were just kind of going through. But then there's this QRAUX. I don't know how to pronounce that. There's pivot, tall, and rank, okay? So because these are all named, we can use the $ to access all of these. So we can just do $QR. That gives us back that list of length 5, right? So there's that matrix. So we have QR. That's that matrix, right? And then we have this and this and this. And so we're just trying to get to tall. So then we just use $ again and call tall, and we get the QR tolerance, okay? The second thing we wanted to get back is the term labels from the model, okay? And I said, this one is a little tricky, and involves pulling an attribute from an attribute, okay? So let's look at this. Let's look back at let me do this, run this again, the structure of M, okay? And then we want to go, what was it again? The term labels from the model. Okay, so here's the model, right? So model is one of the list elements. And so we can see, here's the model. And then when we come down here further, we can see we have this thing, right? Which has some attributes. And then inside of that is term.labels, okay? So the way that I did it anyway, and there are multiple ways to do this, but is I first pulled all the terms attributes. So where's the, maybe I'm looking at this wrong. Yeah, terms, okay. So I was looking at the wrong ones. Here's terms, right? and this is confusing. So you could have pulled these term labels also. Either one would have been fine because this is from the model within the model object, right? But I was actually apparently aiming for this one. So my language was certainly not clear here. But from M model, oh, wait a minute. No, that's the right thing. I'm sorry. Okay. Let me get rid of this again. strm. Okay. So within model, we have this thing. So I am looking at that, right? And then there's terms. Where is terms? Don't. Oh, no, I see. Okay, sorry. I'm losing track of things. So within model, I'm pulling the terms attribute. Okay, so here's all of the attributes, and we have terms. Okay, so what, again, part of how I might do this to start is I would use attributes on M model. Okay, what attributes is going to do is it's going to list all of the attributes for a given object. Okay, so when I do that, you can see all of these different attributes that are associated with it. Okay, attributes M model, we have names, we have terms, we have, which has all these other attributes, we have row names, and we have class. Okay, so this is all the term attributes for terms. So within all the attributes, we have terms right here, right? So this is giving me back just that part. And now I could again do attributes on term attributes. Okay, and we have these different things. And there's term labels right there. Okay, so we have variables, factors, term labels, order, intercept, response, class. So then I could just pull the term labels from that. Okay, a little bit confusing, and I wouldn't blame you if you pulled the other term model in there, or if you got confused on that one. But this is a good example of sometimes things are really buried in those lists that you need to access. And so being able to work with attributes, not just nested lists, can very regularly be helpful. Okay, any questions on that? Okay. All right, so that was number one part, what I'm calling down below A and B. So then from L, this thing up here, right, we're going to use at least two different methods to extract M. Okay, so M is this matrix. Okay, and so we need to use at least two different methods to do that. Okay, so because everything is named, the first way that I could do this is by just using the $sign, LAM, right? Just keep that $sign going. There we go. There's my matrix. Okay, that one's probably the most straightforward. We could also say from L, give me the first element of L, and that's going to have M and V. And then I'm saying, okay, now from that list, give me the first element of that list. Okay, and that returns it as well. Okay, there's other ways we could do this too. Like we could do something like LA1, okay, or LAM, okay. Either of those will work as well. Anybody do it some other way? Any questions on that? Okay. Now, for what I'm calling B, the second part of this, extract the third column of M, maintain the dimension structure. Okay, so I said in class that I would like you to do that without calling matrix or as.matrix or something like that around it. Okay, and so what I was looking for there was for you to first pull the matrix like this, right? Then grab just the third column. So I'm saying give me all rows from the third column, and then I add this additional argument, drop equals false, and that will not drop the dimension structure. Okay, so I get one column in return, whereas if I didn't include that, right, then I would get just an atomic vector in return, with no dimensions. So the attributes would be dropped. Okay? Makes sense? All right. And then for the final one, C, I said extract the score for student 7 in the data frame. There are very many ways that you could do this. This is how I did it. Okay. So we have $$B. That's going to give me the matrix back in return. And then I can tell from this that the 7th row is the 7th student. So I can say, just give me the 7th row. Okay. That works and that's fine. But it's not the most programmatic way to do it. In other words, if this data frame somewhere higher up in my script got changed, right? So this might be the way that I'm doing it to start, and that's fine. But then let's say I'm continuing to work with these data over weeks or months or whatever, and somewhere previously up in my script, I forget that I'm pulling it by this index like this, and I do something that sorts the data frame differently, then this method will fail. Right? Because this is relying on the 7th row being the 7th student. And that might not always be the case. So what we can do instead is make it a little more programmatic. And so this is one way to do this, right? Where I can say LB, right? This thing, and then pull just the student from there. And then say, is that equal to 7? Okay, and then that gives me this logical vector in return, where it's going to be false when it's not 7, and then it's true when it is 7. Okay, and then I can use that logical vector to, I don't know why I have that one there, but I can use that logical vector to subset it now. Okay, so this one now on line 91 does not depend on the 7th row being the 7th student. So if the data set got sorted differently, row 91 would still pull the 7th student, whereas row 88 would not. Okay, so row 91, either one for this, for this lab is totally fine, right? But in terms of thinking about building out robust code that's not going to break, row 91 is much better. Okay, 92 is just an alternative way to show that you could use the brackets to get B instead, and then rows 94 and 95 are alternative ways of breaking up row 91 into sort of 2 lines. This is probably actually a little bit, this is 86, that should be 91, because I've made some other edits up above. But this is actually probably a little bit more readable, I would say, where row 94 is, I would even say stu ID 7, right? So this is the logical, oh no, that's wrong. Stu ID is what I should probably do. Stu ID. IDs. So this is all the student IDs. And then in this row, I can say, okay, now where the student ID is equal to 7. And that gives me the same thing. Okay, so these two lines give me the same thing as this one line. But this is probably a little more readable. Okay. Questions on any of that part? Okay. Moving on. We're now moving to loops. So the first part, I ask you to read in the insurance coverage.csv file, which is in the data folder in the repo, and then split the data by age bucket and sex name. Okay. So I'm asking you to split by 2 variables. All right. So let's do that first. First, this is just the way that I did it. Yours is, I'm expecting to be a little bit different. This is sort of a nod towards where we're going with some of this, but I'm using the fs function and this dirls. Okay. So what this function is going to do is it's going to look in a directory, aka a folder on your computer, and it's going to list the files that are in that folder. Okay. So I'm saying, okay, give me all the files in my data folder. Okay, so this is my path here, data. And then if I don't have this part, then this would give me every, actually, that's just going to give me the directory. But when I, oh no, Yeah, it does. It gives me two things. So I only have two things in there. This first one is the insurance coverage one. And then we also have a directory, which is why it's colored differently, called pfiles_sim. All I really want is this one. So I'm giving it a regular expression, which is just saying, give me a pattern to look for and look for insure. Okay. So then that just gives me the file path to my data set that I'm going to read in. Okay. When you only have one file in there, that's really not helpful. It's just extra work. But where this becomes really helpful is like when we go to P files, which we'll see later in the term, where you have like, say, 80 files that you need to read in, right? And you can use something like this to list all the files that you're going to read in, and then you can loop through those file paths to read them in. Okay. So again, that's just sort of a nod towards where we're going with some of this. Okay. So now we have our file path file, and I'm just going to use read_CSV from readr, and that reads it in. I put a note on Canvas to just use readr, and you shouldn't have had any issues with it. If you use Rio import, you might have had some issues with it because it does have some weird stuff at the start and everything, which read_CSV used to not fix, but it does now, which is really nice. So it makes life easier. Okay, so now I have insurance, and I'm going to split it by my two variables, age bucket and sex name. And notice I just say insurance is the thing I'm going to split, and I pass it a list of the variables that I want it to split by. Okay, so let's look at this real quick. By age, sex. Okay, and you can see we have insurance under 6, male. Insurance 75 plus, male. Insurance 6 to 17, male. And if I go all the way up to the top, right, we get insurance 6 to 17, female. Okay, so it's split that all by those different groups, by those two different groups. Okay, so that's good. And then the next one is use a for loop to calculate the mean healthcare population, so HCPOP, for each age bucket sex name combination. Okay, so within each of these, you can see we have HCPOP. Okay, all I'm going to do is compute the mean of this variable for each of these, each element in the list, basically each data frame. Okay. So, and I want you to do it with the for loop. So to do it with a for loop, remember the first rule of a for loop is you always pre-allocate a vector to store your values. Okay. So I'm going to repeat an NA value, the length of by age sex. Why is it the length of by age sex? Because that's the thing that I'm going to be looping through, right? So I know that my output is going to be the same length as my input being that list. Okay. So that looks like that, just a bunch of NAs. And now we're going to loop through. So I say for I in seek along by age sex. And remember, seek along is just going to be an index from 1 to the length of by age sex. So we get 1 to 18. And then I'm saying for the first element of mean HCPOP, so this NA thing, just imagine, right, for the first time that we're just doing it for the first one, we're going to get the mean of the first by age sex data frame, HCPOP, and then I say na.rm equals true. Okay, and then we're going to do it for the second one, and then the third one. And notice that I have single brackets here, and I have double brackets here. Why is that? Why do I use single brackets on mean HCPOP, but I use double brackets on by age sex? So we're looping actually through two things at the same time. Mean HCPOP1 looks like this, and by age sex looks like this. Right? Yep.
Yeah, because I think HCPOP is a vector, atomic vector, whereas by sex is a list.
That's exactly right. So if you couldn't hear on Zoom, it's because mean HCPOP1 is an atomic vector, and by age sex is a list. Okay. And so we're using the double brackets on the list because, again, think of that analogy with trains. The double brackets are saying, give me the thing inside of the train car. Okay. And so in this case, we're saying don't give me what's inside of it, but put it in there. Okay, put it inside of each train car. Okay, so we're going to basically go to the first train car. We're going to put a mean in there. We're going to come out, go into the next train car, put a mean in there, and etc. But this one, this mean HC pop, is just a vector, so we just fill it out. Okay, so I run that, and we get all the means that look like that. I did put here, you can see how I would do it if I were just manually looping, right? So you can uncomment those and run them if you want, but it should be the exact same. This is basically what the loop is doing. Okay, questions on that? Okay, number 5 says replicate this calculation with lapply, sapply, and vapply. Okay, so to start out, we're going to do lapply, and lapply takes a vector as its first argument to loop through. Okay, so the vector we're looping through in this case is the list. It's our by age sex. Okay, then the second argument is a function that you want to apply to each element of the vector. Okay, so in this case, I'm saying function x. I think it's actually probably better if I said function df. So I'll change that because each element of this by age sex thing is a data frame, right? So I'm saying using df here as just like a placeholder for each individual data frame as we go through there. Okay, so I'm saying the mean df hc pop na.rm equals true, and I run that and we see we get this. Okay, one of the nice things about lapply is it will maintain the names if it can. Okay, so the list that we were looping through, this by age sex, has names, right? When you look at it, it has names here. And so when we're doing lapply, it will maintain those names and tell you which one the mean is for each of those. So you can see basically line 140 and these lines up here for the for loop, they're going to give you back basically the same thing. The only difference is that in the lapply version, it's going to be a list that is returned, whereas in the previous version with the for loop, we're getting an atomic vector that's returned, right? So that's cool. The lapply version is much, much shorter and helps to put the focus on the operation rather than all the code, because it's kind of a lot of code to write for a single for loop. But other than that, they are basically the same. Okay. sapply. Real quick, before I do this, what's the difference between lapply and sapply? What's the fundamental difference between the two of them? lapply always gives you back a list. What does sapply do? Do you remember? Simplifies. Yes. So the S of sapply stands for simplify. Okay, so it's going to try to simplify the output if it can. In this case, we have a list that looks like this as our output. Notice that each element of that list is of length 1, and they are all of the same type. They're all double. Okay, so it's going to figure that out, and it will simplify it down to an atomic vector. Other than the swapping out the L for an S, this code is exactly the same. Okay, I also can swap these out for DFs if I wanted to. Okay, and now our output minus actually having names, which is helpful, is exactly the same as the for loop we did above, but with considerably less code, right? However, as I said in the slides a bunch of times last week, sapply is great for interactive work, and I would highly encourage you to use it. It is not so great for programming because it is less predictable. So if you get one type of input, you can get a list back. If you get a different kind of input, you can get an atomic vector back. If you get a different kind, you might get a matrix or an array or whatever. Okay, so I recommend not using this for programmatic use. Instead, I recommend using vapply. What is the main difference between vapply and sapply? Do we remember? That's exactly right. vapply, you state explicitly what you want the output to be. Okay, so in this case, rather than just letting it simplify, I am saying it must be of type double with dimensions 1, okay, which just means an atomic vector. Okay, so this one is a little bit more verbose because you have to include this additional line, but otherwise it's the same as the others, and you are guaranteed to get back the type of output that you want. If it cannot do that, if it cannot give you back an atomic vector of the type that you requested, then you'll get an error. Okay? All right, good. Number 6 says produce separate plots showing the change in HC pop from 2014 to 2015 for each age bucket sex name combination with a single loop. Set the HC pop axis so the limits equal the overall minimum and maximum values for HC pop. Okay, so number 6, let's start it out here. I'm going to load ggplot. Normally I would put ggplot up at the top, right, with all of my packages, but just for here. Setting my theme, and then here I'm going to set my y-axis range. Because of that second part, I said set your overall to be the minimum and the maximum. So I'm just calling the range function on HC pop. And notice I'm using insurance here, which is the entire data set, not the split by sex and age. Okay, so I call range on that and I get just this vector in response of length 2. So this is the minimum value, this is the maximum value. Okay, now if I were to do this in reality, I would do it like this. So I would say, okay, now let me just work with insurance to start, right? And I'm gonna go ggplot insurance AES. What was I gonna plot the relation between? It was HC pop, the change from 2014 to 2015. Okay, so let me look at insurance real quick. And we have this year variable, okay? So I'm gonna put year on the x-axis, and I'm going to put HC pop on the x or on the y-axis. And then I'm gonna say, all right, now put a line connecting them and then add some points on there. Okay. And it looks like that. So there's a bunch of different points here, obviously. And that's fine. And then I probably want to say y lim, or I go scale, y continuous, limits equals whatever I call that thing, y-axis range. Okay, and that's going to put the limits at that, which it's already there, so that's fine. Okay, so that's cool. That's how I do it for 1. And now I'm going to take that code and I'm going to basically just generalize it to an X data set instead of to that specific data set. So I call lapply on by age sex. And again, I could say df here. So for any data frame, put year on the x-axis, HC pop on the y-axis, and then put a geom line layer, a geom point layer. And then I did change my breaks on the x-axis because notice we have, for the year, we have 2014.25, 2014.5. So we're kind of breaking the year into quarters here. We don't really need to do that. So I just set the breaks at 2014 and 2015. We'll get rid of all of that. And then set the limits to that y-axis range. Okay. And other than that, it's basically the same. And now I could plot all of these if I wanted to. Right, it's going to be a fair number of them, but now we can go back and you can see that the y-axis is staying the same, but each plot is slightly different. Okay. Questions on that? Yep. Yeah, so if we wanted to put a title on it, we could extend this. I'll put a note here. Extend this so it has a title on each. So first, we need to have the years that we're looping through, right? So, or wait, no, what are we? Yeah, okay, this is the thing. So I'll create a thing called titles, okay? And what I'll start out with this is just by saying, what's the names of by age sex? Okay, so now titles looks like this. This is all of them, right? And then I could probably drop the insurance part. So I'll go titles, G sub, find insurance underscore and replace it with nothing in titles. Okay, so now titles looks like this, and you could do this more automatic, right? I'm just doing this pretty manually. And so then I'll just swap this point for a space, titles, G sub. Remember, I've got to escape the period because that's one of the special characters. I'm going to replace that with a space in titles. Okay, so now we're getting there. Now I might try to do this where I'll say G sub. I'll see if I can find a digit 2. And I'm going to wrap that in a thing like that. And then I'll say, actually, shoot. I'm going to get rid of this part. Digit 2. And I'll replace it with digit space 2. Let's see if that works. And put a space there too in titles. Let's see if that works. Yeah, we got a little bit of extra space. All right, so this is really dumb, but that's okay. Last part of this, I'll say G sub, look for any double spaces and just replace them with a single space in titles. Okay, so that is quick. And we got some errors like 75 plus is still not there, and we got under 6 there. So we could clean up that stuff if we wanted to, but whatever, we'll just keep it as that for now. Okay, so now we're gonna take our code up here for our plots. I'll call it plots 2 this time. Okay, but actually, because I'm looping through 2 different things this time, it's gonna be easier to do this through a for loop. Okay, so I'm gonna keep my plotting stuff down here, but I'll say for, actually, I'll do it like this. For I in seek along by age sex, and then we'll call it plots. Plots 2 is going to be a vector of type list, and it's going to be the length of by age sex. Okay, so plots 2 is just going to be an empty list at this point, and we're going to fill that in with each of these. Okay, so I'll go plots 2 I is going to be defined by ggplot, and then we'll say by age sex I, right, each data frame. And then we're going to put year, htpop, blah, blah, blah. All of that is the same. But then we just do plus. Let me fix this. We'll put this down here. That's good. Okay. And then I'll go plus labs title is equal to, and then I can give it this other thing, titles single bracket I, and it's going to be single bracket because we have a vector, right? So we do that, and I got some error in there. Hang on, because I forgot to put my braces. That's why. I have that brace, but yes, that's from my L pie that was left over. Okay, let's try that. Okay, so now we have plots 2. We can look through them. And under 6 male, 75 plus male, D to 17, that's not great. 6D to 74 male. So I did mess up on the titles there, but whatever. You get the idea, right? Okay. Any other questions? Okay. What did I do with that D? Oh, this is supposed to be 1. That's why. All right. Let me just look at like plots. Sorry. Okay, well, that didn't work either. Oh, plots too, that's why. Thank you. 35 to 45. 40. Okay, so that's right now. Okay, cool. Any other questions on that? That part was fast, obviously. We're gonna get to looping over multiple vectors soon. I think next week, actually. Okay, so the next one was use a for loop, save the plots to a folder on your computer. Okay, so this saving part is actually very similar to what we were just doing, where we're going to be looping over multiple things at the same time. Okay, so the first thing that we're going to need to do is I would anyway, create a directory to save all the plots. So I use dir.create. Okay, and then I'm saying here plots. So here plots is going to give me a file path from my home directory to a folder called plots, which doesn't currently exist, but that's what dir.create does. So we can see if I go back here. So I actually do have plots. Let me see what's in there. Oh, it's all of these plots and something else. Okay, so whatever. I could delete. I will just delete this for now. Okay, so we'll delete that. Okay, and then when I do this dir.create here plots, then it creates plots. It for some reason puts it out of order until go back here. There it is. Okay, and notice there's nothing in it yet. Okay, then we need to create two vectors to loop over. So we have our plots that we need to loop over, but then we need to loop over over file paths to save. Okay, so the first thing I'm going to do is create file names, which I'm saying here plots, and then I'm just pasting in, I'm swapping out the period for a dash and then adding .png. So the file names look like this, right? There's the full path, and then it's insurance under 6 dash male, right? Insurance 75 plus dash male, and then up here, insurance 18 to 24 dash female. Okay, so these are all of the different plot names that I'm going to be saving out. And then I just say for I in seek along plots, loop through file names I, so give me the first file name, and then save the first plot, right? With the device equal to ping. And you can add additional arguments here if you want to, like width and height. And this is, again, the exact same as doing, let's say I have something like this, and I do, 1, and then 2, right? And then 3, right? I could do something like that, and that would get me the same result. But instead, I'm just going to go through all of them at once, and that I becomes the placeholder for what I had down below. Okay, so I do that, and you can see them start to fill out here. And then we could go and look at those if we wanted to, but we're not going to right now. Okay, and that is it for lab 1. So as I mentioned, I will post this immediately after class, and you can review any of it that you want. If you have it handed in to Canvas, then you will get credit. I have said in the past that only one person needs to hand it in. Because we're doing it on a completion basis now, it would be best if everybody could turn it in, because it's just easier for me to see, oh yeah, you submitted it, you get credit, right? But for this time, don't worry about it. I'll get it figured out. But for next time, if everybody can hand it in, that would be easier for me. Okay. Any questions on lab 1? Great. Switch my share to here. Okay. So what we'll do today, in terms of the next few hours, I'm going to go through, as I talked about before, I will go through this example of functional programming and sort of what that means in more depth. We'll go through that whole example. and then we'll take our break, and then we'll come back, and then we'll do the additional purrr stuff, and and then we'll have our second lab. Okay, so learning objectives for today. I don't have anything about functional programming stuff, so I'm going to just add one sort of on the fly here that's not actually on the slides, but is to hopefully, when we go through this little example, you'll start to get a better feel for what the essence of functional programming is and how you can use it to solve big problems that scale. Okay, because that's the main thing, is basically everything we've been working on so far in class has always been kind of ad hoc, right? So it's like you can use it to solve a problem at one point in time for one set of data, and then you're good. But what we're moving towards is more, okay, I can build a system that takes in some data and then outputs some stuff, and then that can just kind of exist and it can work as the data come in, or I can run it every so often and it will produce more results. Or I have something that I want to apply to one file, but I actually have 15,000 files, and it would be better if I didn't have to do the same analysis over and over and over again. It'd be great if I could just write sort of the instructions on how to do the analysis and then have it churn through all of them, right? That's what we're hoping to do. So that's functional programming bit. For the purrr parts, hopefully you will see the connection between purrr map and lapply. That is a very direct relationship, as we will see. They are essentially equivalent. There's just a few differences. And then for loops. So hopefully we've already kind of seen the similarities and differences between lapply and for loops. And then understand the 4 basic variants of map. Okay. Again, today is a very intro to purrr. So that's as far as we're really going to get. Oh, I did have a bullet on functional programming, the last one. But that's really as far as we will get with purrr today, is map, which is essentially lapply, and then these variants of map, which will take the place of bapply. Okay. So functional programming bit. What is functional programming? Basically, the idea is that you have some really big problem, right? And you could approach it by just trying to approach the entire problem and trying to address it as well as you could. But very regularly, that ends up with us being in this situation where we're actually being quite repetitive, right? There's some sort of thing that we're doing for one piece of the problem, and then we need to do it again for this other piece, but we need to swap out bits of code because it's not exactly the same, but it's pretty similar, right? And then we have to do it again for this other section that is very similar, but not exactly the same, right? Because sometimes maybe you're wanting to do something with a variable, but you don't know how many levels it's going to have for this specific case, but it does, for this other case or whatever. And so the point of functional programming is to first look at the problem in that way. Look at this big problem and say, okay, how can I sort of decompose this problem into smaller subsets? Okay, what's like a small little piece that I can pull out of this, and then solve the problem for that one little piece. And this is not, I'm not talking about anything else here programmatically. I'm not talking about loops, not talking about functions, anything. Just, can you look at the problem, decompose the problem into smaller pieces, and then grab one of those pieces and solve the problem for that piece only? Okay, so that hopefully seems like it should be reasonable, right? The hard part of that really is the first part of that I said, which is sort of seeing the problem and being able to break it apart into these smaller pieces. Okay, once you can do that, though, you will start to see that those pieces, some of them are going to be replicable, right? They're things that you can do over and over and over again. So from there, you're going to write a function to solve that problem. So you're going to basically figure out the small pieces. Once you get it figured out, you're going to solve it on that one small piece. And then from there, you can generalize it to a function. And then you can take that function and use it to loop through for all cases that have that specific set of problems. Okay, And so you can do this with a bunch of different, like there can be a bunch of different dimensions of the project, and you can kind of build on each piece. And then at the end, you can actually sort of build up. So it's like very regularly, projects have this tree structure, right? Where at the very root, you have all of the, or at the very top of the tree, or like a tree that's upside down, really. You have all of these leaves down here that have all of these pieces, right? And then they kind of all link together, and then these pieces link with these pieces. And then you get all the way on top of the tree where you're really just calling one function, maybe, to solve your entire problem, which then calls all of these other functions in turn, and it all sort of splits out. Okay? So, very quick example, or not very quick, but a fairly quick example. Let's say we're just going to deal with the MPG data set. Okay, super simple data set on miles per gallon for cars. And we want to be able to talk about cars in terms of their miles per gallon. And so we want to calculate the top manufacturers in terms of miles per gallon. Okay, but as we all know, probably, miles per gallon is going to be really dependent on cylinders. So we might not want to just solve this generally, because there might be some manufacturers that only make 4-cylinder cars. And so those manufacturers are going to rise to the top and look really, really good. But actually, maybe if we, looked within a cylinder type, it would tell a different story. Okay, so we're going to start off by trying to solve this problem for one set of the data, which is just for one cylinder. Okay, so we're just looking at 4-cylinder cars here. And then we're going to generalize this so that we can solve it for all cylinders. Okay, so starting out, and you can follow along if you want, but you probably don't really need to. There's stuff later that I will ask you to follow along on, and we'll have challenges and stuff. But for this part, it's probably not super important. Okay, so I'm just going to subset the data so that I have one new data set. And that new data set is just a subset of the original data set that only has 4-cylinder cars. Okay. Next, we're going to filter that data set down so that we only get cars that are in the top 10 percentile. Okay, so from the 90th percentile or above, only those cars are going to be there. Okay, so the way I'm doing that here is I'm using this quantile function, which says, give me the 90th percentile of city miles per gallon, right? And notice, yeah. And so this is the 90th percentile for 4-cylinder cars, because I have the 4-cylinder data set that's being passed in here, right? And I'm saying, give me the 90th percentile for city miles per gallon for 4-cylinder cars. And then I'm saying subset it to where city is greater than or equal to whatever value that is for the 90th percentile. Okay, so what I get back in this case is just 10 cars. Okay, now let's say we want to count from here the unique occurrences for each manufacturer, each model, and tie that with the manufacturer, and each class. Okay, so I can do that pretty easy within dplyr as well. I just say count 90. 90 is the thing I called this back here, right? From 90, count the manufacturers, count the manufacturer and the model, and then count the class. Okay. And so I should have printed these out, but you know what these look like, right? These are just counts. They have one column. So like this one would have one column for the class, and then one column called N, which just has the counts for those. This one, this count model, would have one column for the manufacturer, one column for the model, and then one column for the N. Okay. So from there, I might then want to produce a plot for each of these. And I'm not showing the plots here now, but I will show them in just a second. But I know these are count data frames, right? So I have this count MFR, so count manufacturer, right? And I'm going to factory order the manufacturer by N, putting it in reverse. And then that's going to be my x-axis. And then I'm putting N on the y-axis. Then I'm doing geom call and then doing some colors. So it's basically just going to be a bar chart of the counts. Okay. Same sort of thing here. The only thing I'm doing that's a little bit weird is I'm using this unite one, where I'm basically taking those two columns, the manufacturer and the model, and I'm stapling them together so they're a single column, which I'm calling car. Okay, so car is going to be the combination of the manufacturer and model, and it's just going to be separated by space. And then after that, it's just a geom call again. And then same thing for class, just counting the class. I'm always doing this factory order, but other than that, it's pretty standard. And I'm using scale fill brewer for the colors. Okay, so for example, oh, well, I guess I skipped another step. But so then I have each of these, and I want to assemble them into a single plot. Okay, so you can imagine this would be something like a dashboard that we're going to use to share with somebody. Okay, so patchwork, I talked about it last time. To me, it's one of my favorite extensions for ggplot. It's such an easy way to assemble plots. So I'm going to say plot car. That first one goes on top, and then we're going to divide. So put on the bottom these other two. We're just going to add them together. So we get our manufacturers, our cars, and then our car frequency. Okay, so our car class manufacturer. I probably should have just said class there instead of car class, or I should have put car manufacturer. Okay, and then car frequency. So overall frequency for the car, the class, and the manufacturer. Okay. Also probably could have used different colors down here because that's a little confusing to have the same color there, but whatever. That's less important for the purposes of this lecture. Okay. So that's how we would do it for one single case, right? But now we want to be able to generalize this beyond just our specific use case. Okay, so I tried to do this, not necessarily exactly the way that I would do it, but in a way that it would be clearer based on what we've actually learned so far. And there'll be some parts that we still haven't learned, but I tried to keep it mostly within what we've learned so far. Okay, so to start, what we could do is instead of dealing with just our one single data frame, we could split our data frame by SIL, and that gives us a list back in return. Okay, then we can loop through that list and apply a function to do the filtering for us. Okay, so notice here, this is my split, right? And then for top 10, this is also going to return a list. I'm going to loop through by SIL and apply a function x, where x is just a placeholder for the specific data frame, right? And I'm going to filter x where city is equal to, and see, notice that this code right here looks really, really similar to what I just did, right? The only difference is now I'm applying it within a loop instead of applying it to one specific data set. But that's why we go through that process of solving it on our own without trying to do the loop. If you jump straight to doing the loop, it's going to be much more difficult because you're going to have to be doing your debugging with a list and within a loop, and that can be really hard. Whereas if you just solve it first on one use case, then you can use that same code pretty much in a loop. Okay, the only thing you're going to swap out is just what the data set is. In this case, X, whatever data set it is in the list for the other thing. Okay, so here's top 10 now. We have just the data set, just the 90th percentile for each of our cylinders. Now we can do the same thing with counts. Okay, this is a little bit strange. We haven't done anything quite like this yet, but it absolutely works. Okay, what we're doing is I'm saying function X. Now notice I have all of my counts right here, and that part is again just like what we did before. Okay, the only difference is now I'm also doing that unite part that I did for the plotting in the other one right within here instead of trying to do it in the plot. I could do it in the plot too. That's fine, but that's not what I chose to do here. Okay, then at the end, I have this explicit return thing. I actually don't need that, but what I'm going to return is a list that has all of these counts. Okay, because we have 3 different counts that we're doing for each cylinder. Okay, so I'm having it return a list that has all of those counts. That's going to be a little bit more difficult to work with, but we can do it. Okay, and you can see this is what it looks like, right? So here, very quickly, I called this one MFR for manufacturer, this one car for the model, and this one class for the class. Okay, so for 4 cylinders, we have MFR, 4 MFR, 4 car, and then we'll have 4 class as well. And then we'll jump to the next cylinder and we'll have those as well. But notice this is all for 4, right? So we have a nested list here. For 4 cylinders, we have a list of length 3. For actually 5 cylinders, we have a list of 3. For each of those cylinders, we have a list of 3. Okay, now we can write a couple of functions to deal with this, okay? So the way I'm doing this is I'm writing different functions to deal with different counts, okay? Oh, wait a minute. No, that's not right. So this is a singular function that deals with any count, but it does have to do something slightly different if the var is equal to car, okay? And that's because if we go back here, we have this title, right? And again, you can do this actually through patchwork instead, but this is not how I did it. That top 10% city MPG, that came from this actual plot rather than like an overall title for the patchwork plot. So that's all I'm doing here is I'm saying, okay, well, if the var is equal to car, then add this label onto it, okay? Otherwise, it's just this, which is basically the count thing. Notice there is this bang bang sim. This is non-standard evaluation. So I mentioned this a little bit last time. We will talk about that later. Just for now, know that when you're working with ggplot, when you're working with dplyr, if you're trying to do programming stuff with them, it's going to be more difficult. This is a very common pattern, but you can also use those double curly brackets that I showed you very often to get out of this as well. Okay, so don't worry about that too much if that doesn't make sense. Okay, but the nice thing is we can now test it. Okay, so this is where counts plot is what I called my function back here, right? Counts plot. And then I'm saying, okay, for counts 4, so when it's 4 cylinders, MFR. So this is going to give me the counts data frame for manufacturer for 4 cylinders. And when I call counts plot on that, you can see we get this nice plot. Okay, so it works there. Let's try it on a different one. There it is for 6 with class. That looks good. And there it is for 8 with car. Okay, so it's working great. It worked on all 3 of our tests. Okay, and notice when I was doing my tests, I swapped out the cylinder 3 different times. Each time is a different cylinder. And I did each of the different count data frames and we got what we want. Notice for car, it does say top 10% of city MPG, which is what we wanted. Okay, now we can write another function that calls that function each time. And we're going to use this to assemble the plots. So we're just going to basically, from patchwork, right, use count plots car divided by count plots MFR, count plots class. Okay, and notice the thing that I'm feeding it. It's L. Okay, so my one argument here is L. This is assuming I'm passing it a list that has these 3 data frames in it, these 3 count data frames. Okay, so this is one count data frame, this is a second one, and this is a third one. And for each of those, I'm calling this counts plot function on each of them. Okay, so I can now say full plots counts double bracket 1, and I get my plot, right? I could do it for another one, and it would work. But we can also now just finish up and say, okay, let's create the plots now for all of the different cylinders. So we say lply counts full plot. There's our plots, and we can look through them. So there's plots 1, plots 2. This is for 5 cylinders, so that's why it looks like that. Plots 3, 6 cylinders where there's the most cars, and plots 4. Okay. So again, some of that might be a little bit fast, and there's pieces of that, like the ggplot stuff, that probably isn't super clear. But this is where we're going, okay? Where it's like you can find a problem, you can work with a subset of the data or just a little piece of it. solve it for that one thing. And like, I can't emphasize enough how valuable it is to actually solve it first before you try to write your functions, before you try to loop things. Okay, you should always be actually solving it first. And then from there, after you have it solved, then try to generalize it to the functions. Okay, and when you're solving it too, don't go through the whole thing and solve everything. Try to think through, okay, I solved this part of it. Can I generalize that to a function now? Now I solved this part of it. Can I call that other function to help me solve this part of it? Okay, and so on and so on. All right, let's go ahead and take a break. It is 2:13. Let's be back at like 2:20, so 7 minutes. All right, here we go. On to purrr. So, functionals. We talked about this a little bit when I introduced lapply, but a functional is a function that takes a function as its input, one of its inputs, and returns a vector as its output. Okay, so lapply, for example, takes a vector as its first argument, but its second argument is a function, right? And so it applies that function to each element of the vector, and it returns a vector. Okay, in the case of lapply, it returns a list every time. Okay, so what does this mean? If we load purrr, which has 3 R's, purrr, and is actually loaded from the tidyverse, we can do things like this. Okay, so this is the base, like this is the most basic function from purrr, and it's like probably the main function that you should think about when you think about purrr is map. Okay, purrr map works exactly like lapply. So I say map 1 to 3, and I pass the function rnorm. Okay, and then you can see that it returns a vector as its output, which is a list, and each element of the list is a vector, an atomic vector. Okay, so graphically, this is what's going on. This is what I thought was actually going to be on the previous slide. Sorry, I got a little tripped up. Graphically, this is what's happening, right? We say map, we call a vector, and then we call a function. And what happens is this function gets applied to each element of this vector. Okay, so it turns out like this. Okay, so this is really what's going on when we call this. If we compare to base lapply, you can see that they look identical. And had I have set a seed on here, the outputs would have been identical. So before we talk about that though, what is actually going on in this loop? What's happening? When I call 1 to 3 in rnorm, what's it doing? Do you know?
It's essentially, so 1 to 3 is a list, right? And it's feeding 1 into rnorm, and then it's feeding 2 into rnorm, feeding 3 into rnorm.
Exactly. And so it's feeding 1 into rnorm, and then 2 into rnorm, and then 3 into rnorm. And each time it's going to the first argument of rnorm, which is the n. Okay, so and then the other arguments are set by default. So the mean is set at 0, the standard deviation is set at 1. So we're getting 1 pole from that distribution the first time, 2 poles the second time, 3 poles the third time. Okay, but we can see the syntax looks identical. The output is identical. Had I viewed set.seed, it would have been exactly identical. So why do we need map? What's the point, right? The base equivalent to map is lapply. This is a direct quote from Advanced R from Hadley. And he says lapply doesn't help support these helpers, which we're going to learn about here in just a second. But other than that, they're exact same. So if the only thing that you're using from purrr is map, then don't use purrr. Okay? That's from Hadley himself telling you, the author of purrr, don't use purrr if all you're using is map. Okay? Map is like a builder on top of other things. You will hear people, I think, sometimes talk about purrr, and they talk about it a little bit disparagingly because of this, right? Of this. They don't dive deep into the package. They don't really understand all of the different things it can do. And so they just see the equivalency to lapply, and they think, well, this is a stupid package. Who cares about this package? Why would I ever use it, right? And I can understand that if you're only using map. There are, however, a lot of additional things that you can build on from there that make it nicer to work with interactively and even programmatically too. Okay, so back to the similarities between them. These two lines are exactly equivalent, and you can see that they're written exactly equivalent. The only difference is we've used map instead of lapply, and the results will be the same. Okay, however, and this is still not worth using purrr if this is all you're doing, but this is where we're going to start to see some differences between them. Purrr also allows this sort of helper function syntax. Okay, that's a little more compact. So what we can do is we can, within empty cars, we can use the tilde, right? Just like in a formula. And then that tilde basically takes the place of function x. Okay, and then when we go into our actual function that we're writing, we can use dot x as our placeholder for the thing that we're looping over. Okay, so just to be a little more explicit, the tilde is used in place of function dot x. Okay, normally we use function x, right? That's like a very common one. So they use dot x to kind of distinguish from that. Okay, but if you wrote function dot x, that's the exact same thing as the tilde, and then using the dot x where you want it. So it's just a little bit more compact syntax. Okay, so that's one helper. So we can do this with, by putting the dot x wherever we want. So here 1 to 3 r norm, and then we use, the tilde, call r norm, and then say the n is equal to dot x. Or in this case, the n is equal to 1, and the mean is equal to dot x. Okay, and so then we get one pole from a random normal distribution that has a mean of 1, a mean of 2, and a mean of 3. Okay, versus the n's here. We could also vary the standard deviation like this, right? N equals 1, SD equals dot x. And that's basically it. Okay, so I'm not really going to talk about map all that much more, but in terms of the parallels to lapply, because as I just showed, it is essentially lapply. Once you know lapply, you know map. They're not any different, except that map also has these helper functions, which are nice, but they're not like game changing, right? They're just nice to have. One thing that's a little bit different though also is that you can use map, and you can use lapply for this too, and very regularly do, but you can use map to pull elements from a list. And the way that map will access elements from a list is a little bit nicer and a little bit easier than the way that lapply will. Okay, so this is a rather complicated list for a couple of reasons, right? First, it has 3 lists within 1 list. Okay, and second, we have no named elements on this first one, and then we have x, y, and z, but z is missing on the third one. Okay, so we have z for the first 2 lists, but not for the third one. Okay, so with map, we could extract just the second element of each list like this. So we'd say loop through L and give me so when I say loop through L, right, that's going to loop through each of these lists. And I'm saying give me just the second element. So notice we get 1, 4, 8 in return. Okay? That will not work with lapply. Okay, we get an error. So that's a pretty nice helper function that map gives us. We could instead do something like this, where we say function x and then use x double bracket 2, and that works, and that's great, and there's nothing wrong with that. But again, just kind of a nicer helper function is this map syntax where you just tell it, give me the second element from each vector that you're looping over. Okay. This is just another alternative syntax for lapply. So this is, you're saying the function that I want to apply is the double bracket, and you surround that with backticks, and then you supply an additional argument to those double brackets, you give it 2. Okay, so that's another sort of briefer one, but I'm showing you this lapply stuff mostly as just the parallels to map. I'm not necessarily suggesting that you write your code like this. You can, it's fine, but I'm going to mostly be recommending that you use map because I still think that this is the easiest of them to write. Okay, and as we keep going on, I think you will see there are many other benefits to using purrr, and so if you're using purrr anyways, you might as well do that, right? Okay, you can also with purrr extract by the name in a very similar way. So I'm going to loop through L and I'm going to pull Y, right? Y was that third element in the list, right? The first was unnamed, the second one was X, and the third one was Y. And Y was there for all of them, so we get this back in response: 2, 5, 5, 6, and 9, 10, 11. Okay? This is sort of strange, but kind of nice. Sometimes I want to return, I want to basically subset what is returned. So here I'm looping through L, right, and I'm getting all of Y. And now maybe I want to say, actually, just give me the first element of Y, okay? Because Y is of length 1 for the first one, and 2 and 3. I don't want all of those. I want just the first element of Y back. So we can do that by just passing a list where we're saying, give me Y, and then give me the first element of Y. This is a little tricky, and this is not something I do a lot of, but if you can remember it, which I tend to not, but if you can, it's really nice brief syntax to subset sort of in 2 different directions at the same time. You're first grabbing from the list, and then you're subsetting what you grabbed all sort of at once. Okay, purrr variance. So that's the basic map, right? That I've hope is made abundantly clear is very similar to lapply. There are also now 4 variants of map, which are vapply alternatives. Okay, these are map double, map int, map character, and map logical. Okay, so obviously it's LGL, CHR, INT, and DBL, but I'll just refer to them as the actual types. Okay, and so you can probably guess where this is going. Rather than having it always return a list, it's going to always return one of the 4 fundamental atomic vector types. Okay, so basically now through map, you have 5 functions to do what in base R we did with 2 functions. But I would argue it's much easier to remember the syntax for those 5 functions than it is for those 2 functions. Because with vapply, you have to remember function and then the type double fun equals and then double parentheses 1 or something like that, right? Which is a little obtuse. If you wanted to do that with purrr, you just do map underscore double. Everything else is the exact same. Okay, so you just basically add the type to your map call, and you get the type that you want back. Okay, so let's just remind ourselves what this list looks like that we were working with earlier. Okay, so list of 3, where we first have a list of 4, no name, and then XYZ, then a list of 4, no name, XYZ, and then a list of 3, no name, XY. Okay, and these are first three are numeric for all of them, but then Z is a character for the first two and doesn't exist for the third. Okay, so we can go through this and say map double L give me X, and it's just like map, it's going to get X for all of them. But then because I've used underscore double, it's going to return an atomic vector of type double. Okay. And similarly here, I could say map double L, give me the first element, and it will return an atomic vector of type double with the first element. Coercion will occur if you get a different type, if it can. Okay, otherwise you'll get an error. So, for example, if I do map character on L and I pull X, it can coerce those numbers to characters without any loss of information. So it will do that coercion for you. Okay. Otherwise, if it's going to lose information, it will not do that coercion and you will get an error in return. The other thing is you will also get an error if the element doesn't exist. So we have Z missing on the last list in our list, right? And so if I say map character L give me Z, I get this error stop bad type. Result 3 must be a single string, not null of length is 0. Okay, so that's annoying. Well, we can fix that pretty easily by just setting a default value. Okay, so instead of saying just map character LZ, we would say map character LZ and then dot default is equal to NA underscore character underscore. Okay, notice this is sort of weird, but I'm very explicitly here saying that I want the NA value to be of type character, not just a generic NA. Okay, and that's because I am saying with map character that I want all character values in return. So I want my NA values to assume that they are missing character values, not missing numeric values. Okay, so very quick note on missing values. I used NA underscores character underscore NA. Generally, not just when you're working with purrr, I think it's best to specify the type of missingness that you have, because as a general programming rule, generally, right, the more strict you can be, the better. Okay, so if you can be very, very strict about what you want, then it will either work because it will be of that type, or it won't work and you'll know why. And it will happen very quickly usually. Okay. BaseR is very strange about this though. So character is in a character, integer is in a integer, but then double is NA underscore real underscore. Okay, real is another name for double in other programming languages. Float is another name for the same thing. Okay, and for some reason, well, I can tell you why. I don't know the exact people, but R is open source, right? It's developed by a bunch of people, not just one individual person. So especially in BaseR, you will run into things like this a lot, where one person called something double and the other person that implemented the NA values called it real. And they're the same thing, but this should really probably be NA underscore double underscore, or we should always be referring to them as real, type real, instead of type double. But whatever, they're inconsistent. It's just, you just have to get used to it, okay? And then the strangest one, I think, is this logical one, which is just NA. So there is no NA underscore logical underscore. If you want to know why, you can, there's a link here that explains it more. I've read it before, but it still doesn't make a ton of sense to me. But if you do type of on NA, you'll see it's logical. Yep.
So it seems like there's also an NA complex.
Yes. So there are two other types of atomic vectors besides the 4 that we're working with. There's type complex and type raw. And they're so infrequently used that I just don't think it's even worth discussing. So if you want to know more about those, you can look at Advanced R and read about them. But I've only dealt with type, I don't think I've ever dealt with type complex, like ever. and I've dealt with type raw like a few times ever. I mean, it's super rare. So, and these ones I use all the time. So that's why. Any other questions? Okay. All right. More quick examples. This is now where we're getting to the point where I'd like you to follow along. So I'll give you 30 seconds here. Please get RStudio up and running if you don't already have it up and running. And then copy this code and put it in your script so you're ready to go. You can run this. We're going to use this for additional things as we go on. Okay? On all the slides, they should have this copy code button. So you can just click that and pull it into your RStudio. Okay, so I'll set a timer on my phone for 30 seconds. So hopefully you have that. What I'd like you to do now is, here's var1, right? I'd like you to compute the mean for var1 in each data frame. Okay, I've given you 4 minutes here. That might be a little strong. So I'll check in on you as you go, but try to use this data frame or this list of data frames and compute the mean of var1 for each data frame. Okay. Okay. So this is the way that I did it to start. Basically, we have our df list, and then I'm using my tilde to mean each data frame, right? Function.x, and then I use .x to actually mean each data frame. So I'm calling the mean of .x $var1. Real quick, I want to just grab this, and then I want to go here locally, and I need to switch my share though. Otherwise, Manuel cannot see, and neither can my recording. So we'll go here. Okay, so here's my data frame. Let me do session restart R real quick. Get rid of this. Here's my df list, right? So there's quite a few different ways that I can do this. I can go map df list, and then I could say mean.x $var1, as I did. Oops, but I gotta go per map, right? That's how I did it in the slides. I could also say, give me, the first column, because that's how we're going to subset the columns, right? Or I could even within there say var1, right? And that would also do it. So any way that you can subset a data frame, you can use that here. .x, remember, is just your placeholder for the given data frame. Okay. All right, so back to the slides. If we wanted to return a vector instead, all we have to do is, instead of using map, we would use map underscore double. Or in this case, actually map underscore int would work too, because we would, usually a mean is going to be of type double, but in this case, they're also integers. So that would be fine as well. We could try out coercion if we wanted to. So I can call map character, map logical. Notice I'm getting an error that's saying can't coerce element 1 from a double to a logical. So it's going to give me an error. But if I wanted to, really, which I don't know why I would, but I could actually call as.logical inside of my function, and then that would coerce it inside of there to be logical, and then it would work, right? But what we're getting back is nonsense, because anything that's not 0 is going to be true for coercing numbers to logical. But if we wanted to, that's how we could force it. Okay, more examples. Okay, now we're going to work with a data set called economics, which I think is just in tidyverse. So let me come here real quick. Go library tidyverse. And then I'll go economics. And there it is. Okay. So you should have economics data set. Okay. And what we're going to do is we're going to first create this column called year. So I'm just going to copy this code, come over here, and I'm creating a thing called econ, where I'm saying from Luber date year on date. So notice now I have this additional column for the year, which is just parsing the year from this date. Okay. All right. Now we're going to split it by year. Okay. So split econ by econ year. And you can see we have from 1967 all the way to 2015. So we have all of these different data sets. Okay. All right. Now, what I'd like you to do is fit a simple model to each. So we'll talk about better ways to do this, not statistically, but just programmatically later. And this isn't really the best way to do this statistically, but it can actually be very helpful diagnostically for more complex models to just fit a simple linear model to subsets of your data. And it's a good illustration of this thing. And I think it's pretty good. So here's what we're going to do. What is the relation between personal consumption expenditures, the variable PCE, and the unemployment percentage over time? Okay. Problem is we don't have the percentage. Okay. So we have to compute it. So you try first using that data set that you just had, try to compute the percentage, and notice that this must be done with the split data set because we want this percentage to be relative to that year, not relative to the entire data set. Okay, so 4 minutes again, try to do that. Try to add a new column to each data set in that split data set that has the percentage. Okay. Okay, so I'm going to start out by solving this for the whole thing. Okay, so let's look at econ again. If I want to compute the unemployment percentage, then I have this unemployed column, right? And I would probably just do it like this, right? I would say something like mutate unemployed PCT percentage is equal to unemployed divided by the sum of unemployed, right? And that is going to give me a different percentage for each of them. And if I really wanted to be, that's actually the proportion, right? I could go times 100. And there's the actual percentage. Okay? Does that make sense? Questions? Yeah.
Sorry, isn't population pop?
Oh, pop. Yep, you're right. Divide by pop. That's better. All right, so that's the unemployment percentage. Okay, so that's how I would do it for the whole thing. Okay, so if I want to do it for by year now, then what I would do is, and actually it probably doesn't matter if I do it by year or not because of that pop column. But what I would do is I would go by year. And then I could, shoot, let me do it like this. I'm going to say map by year, tilde, and then I just use that .x in place of econ for this code. Okay, I can bring it back up here. But I'll just say .x like that. Okay, and then we have this unemployment percentage column on each of them. Okay, so this, we could call this unemployed, whatever. Okay, that makes sense. Are there questions on that? That one I would have expected would have been a little more difficult than the previous one we did. So if you didn't get it, don't worry about it. But again, this is why I do things up here first, is so I can debug. And then once I get that, then you're basically just going to copy that code and put it in a loop, but you're replacing the data set that you used with your .x in your loop. Okay? So, so here we go. Mutate .x % is equal to unemployed divided by pop. And there we go. We have %. Okay? All right, now let's try to fit the models for each of them. So this is what the model should look like. Okay, it's almost 3 o'clock. I want to make sure we have time for the lab. So we're going to go for 10 more minutes and then we'll stop regardless of where we're at and jump to the lab. Okay, but this is the model that I want you to fit. Okay, try to fit that model to each data set. Okay, 3 minutes. Go ahead. Okay, so what we're going to do here is we're just going to map through whatever our object was that we applied, that we created before. I called mine in the slides anyway. Perk for %, right? I use my tilde, lm, put that formula there, and then I just say data equals .x. And what I get back is a list of 49 different models. Okay? All right. Now you can extract the coefficients with the coef function. So I'll give you 2 minutes, try to extract the coefficients from all the models. So basically you're going to apply this coef function to each model. Okay, 2 minutes. Okay. All we have to do in this case is do map mods and pass it the function coef. Okay, if you wanted to, you could do tilde coef.x with the parentheses, but this function is being applied to each model. So that's all we have to do. Okay, this part is just showing the first and second coefficients and then the last one. So we have 1967, 68, and 2015. Okay. This is probably the last one we'll do, and then I'm going to walk you through a few other slides, and then we'll jump to the lab. Okay. So what I'd like you to do is try to extract the slopes. So not the intercept, right? So if we look back here, we have the intercept, and then we have PCE. So basically, this one, this value for PCE, that's what I'm asking you to extract. Extract that for all of them. Okay. 2 minutes. Give it a try. Okay, so here's how I did it. All right, my thing I created back here, I called it coefs. Okay, so I'm just going to loop through that and then say, give me the second element. Okay, notice I'm using map double here because might as well, right? All I'm doing is returning a single vector at this point of type double. So I get a single vector back in return. From there, then we can do things with this, like I've put the year in a tibble with the slopes, and then I can plot the relation. So here's like the histogram of the different slopes across the years, right? That's cool. But this is the part that I actually wanted to show you, is that very regularly you can use piping to solve this same sort of a problem, just like you would with a data frame. But at each instance, you're passing a vector instead of a data frame. Okay, so I have by year, and I'm going to pipe that to map. Notice by year becomes the first argument of map here. So I go straight into the tilde and do mutate .x, where the % is equal to employed divided by pop, right? And then I can pass that to another map and fit my models. Pass that to another map, extract the coefficients, and then pass that to map double and grab the second one. And that's how I get all of my slopes. Okay, so I just fit whatever it was, 59 models, and pulled the slope from all of them, which is pretty neat to be able to do in that amount of code, I think. Okay, we don't have any more time to practice, so forget about that. So it is time for lab 2. Also, just a reminder, we have that midterm quiz next week. Okay, so just review the slides and stuff. It's not that big of a deal, but if you are stressing about it at all, let me know and I'll try to calm your nerves, because there's really not that much to stress about, I don't think. Okay, let's look at the lab together. So we'll go to assignments and then lab 2. Okay, so similar to lab 1, but focuses specifically on looping with purrr. Okay, so part A, this is all going to be quite similar to what we just did. This is just a URL to a data set. Okay, and then you're going to load in that data set with this code. And then when you run head benchmarks, you should see this. Okay, so this is just code that you will run. Okay, this is some things describing the code. So SID is the student identifier. Cohort, there's multiple cohorts of students. Their special education status, their race/ethnicity, their FRL, which is free or reduced lunch status, their English language learner status, and then the season the assessment was administered. So students have between 1 and 3 assessments. So the assessments were administered in the fall, winter, and spring. These are all simulated data, by the way. And then their reading and or math score. Okay. So I'm asking you in this part to recode wave or recode season into wave. Okay, so I've just given you the code to do that. You're taking benchmarks. You can change it to a table if you want or not. I prefer that, but whatever. And then mutate where wave is equal to case when season is equal to fall, then it's going to be 0. If season is equal to winter, then it's going to be 1. Otherwise, so true, that would be spring, right? It's going to be equal to 2. Okay. Then what I'd like you to do is fit a model like this for each student. Okay. So remember, I said some students have 1, some students have 2, and some students have 3 administrations. If they only have 1, then you're going to end up with missing data on their slope coefficient. So that's fine. You just won't end up using those. Okay. And then what I'm asking you to do is reproduce this plot. I've given you a bunch of code here to work with, and you just basically need to fill it in. Okay, so you're going to fit that model and then reproduce this plot down here. And this is the code that you're going to start with. Okay, so you can drop any cases where the slope value is NA. So that's any case where there's only 1 student, the student only has 1. And then you will need to put these in a data frame with an ID variable that identifies each student. And then it doesn't have to be their SID, but it does need to be an ID. Oh, that's strange. That shouldn't look like that. So then just fill in this, okay? And then you should be reproducing something that looks very, very similar to this. Okay. Part B, this is from, so part A should be really similar to what we just did. Part B is going to use this recursive package, which is basically just a data set to help you learn how to use purrr to deal with lists. So there's this list inside it called SW films, Star Wars films, okay? And I'd like you to use that list to identify how many characters were represented in each film, okay? So basically, you're going to need to inspect that list, and then you're going to need to do some operations on that to count the characters for each film, okay? And then for the second one, same thing, but with Star Wars species this time. And this one has 2 parts. Identify species that have known hair colors, okay? And B, identify what those hair colors are, okay? Part C is going to be a little bit new and possibly a little tricky, but it is a very real world application, just in a not very real world sort of output. Okay, so what we're going to be doing is we're going to be working with a web API, which is called a REST API in this case. And so if you look at Star Wars films, for example, and you look at characters 1, you'll see that there's this, it gives you this URL in response. The first time I wrote this lab, we did this API call stuff with the Star Wars API. That API is since broken and it hasn't been maintained. So there's a different API we're using now instead to do all the same sort of stuff, but instead of with Star Wars, it's with Pokemon. Okay, so you can check out the documentation here. Let's do this real quick. So here it is. This is what the API looks like. It returns JSON data, but we're going to actually, because we're working with it in R, you can do this content parsed, and it will then return it to you as a list instead of JSON. Okay, so you'll need to load the HTTR package, and then you can run something like this, and that would give you the data for the first ability, okay, for Pokemon. So this last part, this 1 is just an index for the ability. So this is for the first one. If you replace that instead with a 3, you would get the data for the third ability, whatever that is, okay? So we can identify what the specific ability is for 1 with like ability 1 name, and you can see it's stench, and the length ability 1 Pokemon. There's 10 Pokemon that have that ability, okay? So what I'd like you to do is use purrr to write an API call like this, okay, to obtain data on the first 5 abilities. Okay, 1, 2, 3, 4, 5. Okay, we're only using the first 5 to make it go fast, but it could go on forever, right? Then use the parsed data to create a data frame that has the given ability, whatever it is, and the number of Pokemon with that ability. Okay, so you'll list, here's the first 5 abilities, and then here's the number of Pokemon with those abilities. Notice that I'm not asking you which Pokemon have those abilities, just how many. Okay, however, for up to 1 point extra credit, you can also list the Pokemon that have that ability. I will warn you, this is extra credit for a reason. It is not easy, but you can give it a try if you want. Okay? Any questions on any of that? All right. Please do feel free to work in groups again. And you have a little over half an hour in class. And then obviously, if you don't get it finished in class, you have to complete it on your own after that. Okay?